Great. All right. So today we're going to talk about dam breaching. This is a 2D slash 1D 2D class. We have an entire class dedicated to dam safety, but it just as the use cases developed, it turns out that it is actually easier in a lot of cases to build a 2D model of a dam breach than the old 1D way. And so it just becomes kind of central to when we talk about 2D and especially 1D 2D connections. And so we've kind of folded that into this part of the class. And so I'm going to do 3 things in 40 minutes. There are 6 different ways. There's actually more. You could actually do the combinatorial math, but there are 6 primary ways to set up a dam breach configuration with all the different options we have in RAS. And so we're going to kind of lay those out and give you the pros and cons. And then I'm going to give you a very brief overview of how to put in breach options and parameters. The bonus content tonight, I have a 28-minute video that goes into how to estimate these breach parameters, and in particular, the 2 really difficult ones, width and time. And then I'll just, we won't even do the slides. For the last 6 minutes, I'll open up RAS and we'll just kind of look at a few of the ways to, visualize breach results. These aren't going to be dramatically different than how you visualize other 2D stuff in RAS. So we'll just give you another shot at that. There is one or two things that are special. Okay, so first, how do you model a dam breach in RAS? Well, you have many options. At least 6. Let's go through them. So I give this lecture in the 1D dam safety class. And in the 1D dam safety class, you're only limited to a paltry 2 options. And the idea here is that when we first started out, you would just make you would just have a 1D model with all cross sections, and you'd put an inline structure in there, and then you'd fail it. Kind of the pro tip is that if your reservoir isn't super elongated, so that you don't actually care about the change in stage along it, you can actually save a bunch of runtime and a bunch of stability by just making your reservoir a storage area, a 0-dimensional model, and modeling the downstream impacts with the cross sections, which is what you're actually interested in. Okay, so that's before we even get to 2D. Those are the 2 kind of historical options. And so here's everyone's favorite Bald Eagle Creek. You'll see this is the way, if you've done dam breach modeling, this is probably the way you've done it. You have an inline structure here and a bunch of cross sections. Maybe you have some levees or lateral structures and some storage areas that simulate the population centers or the tributaries. But this is the classic way to do it. The way we teach in the 1D class is that, well, you can get away from all of the instabilities upstream of this dam and save a bunch of runtime if you just model that as a storage area. But again, that's all just within the 1D model. So nothing new there, but you're in a 2D class. And so what does 2D bring to the table? Well, 2D brings to the table a lot of precision, accuracy, and stability. Because as you've heard, the finite volume solution and scheme in 2D is more stable than the finite difference scheme in 1D. And stability is never more of an issue than with a dam breach. If you've done any dam breach modeling, you have become very familiar with the red bar of death. I'm not sure I've ever run a dam breach model where I didn't get the red bar of death, at least in my first 10 times, right? And that's because you're shocking the system. Differential equations they're generally friendly, but when they see a discontinuity, they get pretty persnickety. And so that's why your model fails. And so having the 2D solver in there can be really helpful. So what we can do for our third and fourth options is just take this downstream area that we're generally most interested in. We're generally most interested in the downstream impacts of a dam failure. And incidentally, I do more dam removal than dam failure, so I will say dam removal at some point instead of dam failure. Just pretend we're talking about dam failure. What we're most interested in is the downstream impacts of the dam failure. So instead of modeling that with less stable and less accurate cross sections, we're just going to switch out a 2D area down there. And so here's a classic configuration where you have 1D cross sections upstream in your reservoir, and then you have a 2D area downstream. And we're still using an inline structure because as long as you've got cross sections anywhere in this connection, you have to use an inline structure. And so if you're using an inline structure in any of these configurations, there absolutely must be 2 cross sections downstream and upstream of your inline structure. And so this is a kind of classic configuration. Whether you're connecting cross sections to a storage area, your inline structure can never be the last thing. And it also can never be the penultimate thing. There needs to be 2 nodes, 2 cross-section nodes between the inline structure and either the storage area or the 2D area downstream of it. But you can only see one here because as you learned in my lecture last night that I'm sure all of you were attentive to at normal speed, maybe even some of you slowed it down to get more content out of it. You have to align your final cross section with the boundary condition to make sure you're not double counting or introducing instabilities. Nothing's more kind of numerically interesting than watching a dam breach happen. And so here's a kind of a classic dam breach where we have cross sections upstream and a 2D storage area downstream. And you just see we get lots of resolution in this downstream area, and we get more stability. The cost is runtime. You know, this is going to take a lot longer than a 1D model, but you'll probably buy that runtime just in simulation time. So far, or these first 3 options, they all have cross sections in them, and so you're going to use an inline structure. But as soon as we switch to option number 4, where you have a storage area upstream and a 2D area downstream, which is going to be your most stable and which is going to be your most stable configuration and is also going to run a little faster than this one. Now you're going to switch to the storage area 2D connection. Now I know that Steve hit this in his talk, but it's worth saying again. In general, if you want to build any structure in a 2D model, you're going to use the storage area 2D connection. That's not entirely intuitive because it has the word storage area and connection in it. And so Steve in his lecture renamed it hydraulic structure. It's just helpful for you to think, if I ever want to build any structure of any kind in my 2D model, the storage area 2D connection is where we want to go. That's the first choice. And so in this case, we're doing it exactly as it's named though. We're connecting a storage area to a 2D area. It's a storage area 2D connection. And so here's a classic, this is a pretty classic approach because you're going to save the runtime upstream by just doing that as a reservoir, and then you're going to get full realization of stability downstream as a 2D area. This is often the preferred configuration. And then between them, now there are no cross sections involved. There's no inline structures. It's a storage area 2D connection, which has all of the breaching features of your inline structure. And the interfaces are almost identical. And so that's how you connect those. Okay, so how do you do this? Because this is kind of the primary workflow, so we'll describe it a little bit. You're going to draw your storage area and enter its data. And then you're going to draw your 2D flow area and create the mesh. In your workshop, there are kind of 3 ways to do this. You can freehand it. You can do it artistically. You can draw a dummy shape and then copy and paste coordinates, which you'll get a shot at in the workshop. But really the main workflow, the modern workflow, and we actually updated the workshop this time to do it, which is why you'll have to download some GIS data, is just import shapefiles. And you can import shapefiles for both of these. And then you use the storage area connection and you draw a structure looking left to right downstream. I know we say this all the time, but if you don't do this in this particular application, it's going to cause you trouble. And I can tell you that because in one of my tries, I did it wrong and it plagued me. I ended up starting over. All right, and then you have to tell the model where is from and where is to. You know, we're talking about the downstream direction, but there's no stream center line to tell the model what's downstream. And so you actually have to give the storage area 2D connection that sort of directionality. And then any gate data, you define the where and enter any gate data. Okay, so this is what the storage area 2D connection looks like. And if you think, wow, that looks a lot like the inline structure editor, that you're exactly right. We're trying to make these things as similar as possible so that the workflow's the same. You're going to have an upstream connection and a downstream connection. That's different. This is different. We'll talk about that in a minute. But then if you want to breach, you press here and it will actually take you to the plan data. We'll talk about that in a little bit, but that's where you define the breach parameters. Okay, so here is a storage area to breach simulation. You can see we get the spillway flow first, and then we end up getting the breach. This one might not actually breach. I think this one just you get like really significant spillway flow. That's great, but this is a 2D class. And so, why would we even use a storage area? Well, we would use a storage area to save runtime if we're not really interested in inundation upstream. But you can also go 2D to 2D. And if you go 2D to 2D, you can save runtime by making your upstream much coarser resolution. And the reason you want to do that is that the storage area not only assumes one water surface across the cross section, it assumes one water surface in all directions. And so if there's any sort of slope on your water surface in the storage area, or any sort of like pooling or anything like that, then a 2D area could be really helpful. And a really coarse resolution with a few break lines could give you a lot of resolution for not a lot of runtime. And so connecting a 2D area to a 2D area is another way that's becoming a common workflow. And so again, here you're going to use the storage area 2D connection, but it's just the 2D connection part that you're using. And so here you just create two storage areas and connect them with a 2D connection. And this is like what we talked about in the module last night. And so here we have two storage areas with different resolutions, and the 2D connection is the downstream boundary of one and the upstream boundary of the other. And so here you're going to get much more realization in the upstream reservoir, and you're going to get all the stability and resolution that you want downstream. The final option is that you don't actually have to use two different 2D areas with that are connected discretely. You can just make the whole area one 2D area and use a storage area 2D connection. And in this image, I've got that all as one. Cell size. But how could you actually make these a different cell size? Let's go to the chat. How could you actually introduce a different cell size in a model that's all one 2D area? Everyone's got the right alliterated answer. The refinement regions. You could go in and put a refinement region in the area, and it wouldn't even have to be the whole downstream area. It could just be the population area, or the place where you're interested in impacts. And so there you go. Here you have one 2D area for the whole reach, and then you just go put in a storage area 2D connection. And this is where that language does start to get weird, because you're not actually connecting anything, are you? And has nothing to do with the storage area. It's an internal hydraulic structure within your 2D area, but we've maintained the terminology, so you just need to get used to it. And so here is a single 2D area. You can see it all has the same cell size, but then we've gone in and drawn in this storage area 2D connection and enforced it, so we have the orthogonal cells along it. And so here you can see that, we've actually been very careful about tracing the high ground. We get, detailed flow over the storage area, over the spillway, and this one will actually fail. And so you don't end up with any instabilities as you pass water between structures or between areas. And it turns out to be a pretty elegant solution. And so I remember when Gary, I don't know if Gary told this story. I think I've been in most of the class. So, but when Orville was looking not great. There was a time when the Orville spillway was, we were not sure what was going to happen there. I remember Gary just came in on the weekend and he just built a 2D mesh, and he just a single 2D mesh, and within 3 hours he had a simulation because doing detailed modeling, getting all your break lines right, that takes some work. But you can get up and running very quickly with just a 2D area. Okay, so those are the 6 dam breach model configurations. I'm sure that we've got three by 3 here. There's other combinatorial ideas that you could come up with, but these are the main ways that it's done. For you generally want your accuracy downstream, and you want to save your runtime upstream. Okay, so next, the breaching options and parameters. In the dam safety class, we spend a lot more time on this because this is really where these are the hard choices you're going to have to make. You're in the world, you enter my world here, the world of erosion and sedimentation, where let's just say we're not as precise as engineers would like us to be. But you have to come up with some parameters for this. And so I'll just very briefly walk you through this. You have to make a couple of categorical decisions before you enter any numbers. The first categorical decision you have to make is your failure going to be overtopping or piping? And I show examples of both of those in the video tonight. And then how do you want to fail the structure? Do you want to fail it based on a certain stage? Or do you want to fail it at a certain time of the simulation? Or there's this other option that's sometimes it's not when the water gets up to a certain stage that fails the structure, but if the water gets up to a certain stage and then stays there and saturates the structure, then you're going to get a blowout. And so you can use that timing stage combination. And then we have other ways of, then the question is, how should the breach progress? Does it happen immediately? Does it happen over as the breach occurs? It's probably not instantaneous. Sometimes we talk about concrete dam failures as instantaneous because they just fall over, but any earthen structure is going to take time, even if it's not a lot of time, even if it's 10 minutes. That matters for what your peak flow is going to be downstream. And so is that progression going to be linear or nonlinear? And then we have a couple of quasi-physical approaches to compute that I talk more about in the video tonight. Okay, so how do you get to the dam breach? This is confusing, because when you think about adding your breaching parameters, you're adding your breaching parameters to a structure. And the structures, whether it's an inline structure or a storage area 2D connection, those are in your geometry. And this is what's confusing. The dam breach parameters are not in your geometry. They are a plan level feature because it's something that happens in runtime. It's part of your simulation. And so you can add breach data through the geometry editor, but see how it says there, plan data? It's actually going to open your current plan and populate your current plan with those data. Or you can just go to the options of your plan and define them there. And this sometimes gets weird because sometimes you'll have a geometry associated with 2 different plans, and you'll change or you have one plan associated with 2 different geometries. You change it one place and it unexpectedly changes or doesn't change in the other place. And that's just because of the one to many, many to one that happens between geometry and plans. Okay, if you didn't follow that, just the takeaway is that if you change your plan data in one place and then open it up in another place, make sure it has or has not changed according to what you wanted. Okay, that's what I want to communicate there. Okay, so and then in the storage area 2D connection, same thing. You can get to that through the actual connection editor or through the plan data. The other thing that you'll do this in your workshop, but that is kind of new with 2D, is that we need to make sure that your 2D structure, that the spatial center line and the length of your structure match. And that matters because we're using this for the upstream boundary condition. And so very helpfully, Mark has put in this editor some numbers to help you see if those match. This is not incidental data. You know, sometimes there are numbers that show up places in RAS and you're like, oh, look, numbers. I don't care about numbers. I like pictures. But these are numbers you actually want to pay attention to. And the idea here is that your center line station and your weir length should be the same. Now, if you're just adopting your weir length from your terrain data, that's fine, you know, but probably what you're going to go in and do is you're probably going to go and overwrite the terrain data because it's not going to actually reflect the actual geometry of your dam. Terrain data can be great, but they're not great for actually the dam geometry. And so you're probably going to go in and overwrite that. And when you overwrite that, you want to make sure that your weir length and your manual weir length and the digital weir length or the GIS weir length are the same. Okay, so then you're going to enter your breach data. We'll talk about this in the video tonight, but you need to turn on the breach. A lot of times you'll run the breach and it won't run, and that's just because it hasn't been turned on. You have to opt into that. And I say sometimes like 60% of the time, my first breach doesn't run because I forgot to click that button. So if you do that and you feel like, oh, that's silly, just think RAS developers do that too. But the option is for it not to be there and you not to be able to turn this off. That's not an acceptable option. So I think this is still the right choice. You're going to choose your breach method. This is primarily what we're talking about tonight. There are 3 different methods for choosing and computing these parameters. And kind of the most common is just to put them in. And so if you just enter these, well, then there are a couple that are really hard. The breach time formation and the final bottom width are really hard. And so you're also going to choose if it's a piping or an overtopping failure. The way this is going to work is you're going to have a prism that's going to grow in your structure over time. But if it's a piping failure, you're essentially going to have a culvert, or actually more actually a gate, because we use the gate equation that's going to grow over time until you get a collapse. And then it's going to turn into a overtopping failure. And this prism is just going to grow over time according to the maximum bottom width and the time of formation that you give it. There's also breach repair options. If you're running a super long-term simulation and you fail your dam or your levee, you can actually go in and fix it so that you don't have this gaping hole in your levee for your long-term simulation. The 2 really difficult parameters to come up with are this final bottom width and the time of formation, the breach formation time. And so we'll cover this in a lot more detail in the lecture tonight. I'll actually introduce you to these equations, but we've added this parameter calculator. There are a number of regression equations that are available to compute those 2 parameters that are just very difficult to estimate just out of the air. And so you can go in and put in a little pretty basic information about your structure. And then we've got 5 different equations that will compute those most difficult parameters, the breach bottom width and the breach development time. And we've even added a helpful button to populate those if you choose one of these equations that you want to use. Probably you're going to choose most of these equations and run it with most of these equations because they're going to be different. And that'll show you how that's a sensitivity test that'll help you understand how these parameters affect your results. You can also do simplified physical breaching, where you can introduce a velocity and downcutting rate. so that as you're in a widening rate versus velocity, so as your breach grows, it's a kind of classic differential equation. As your breach grows, it's going to grow more slowly. As you've got more area for flow, you're going to get less velocity, and your erosion rate will decrease. And you can't really do that with the other options. And so this was Gary's brainstorm probably 5 or 6 years ago. Is, hey, let's just allow users to put in these rates. And it's a little bit fields of dreamy. What I mean to say is, if you build it, they will come. When Gary first put this in there, no one had these data, right? But now that this is in there, people are like, well, let's go and develop some data. And there's some documentation in the RAS unit, and I think the RMC has done some work so that there are some data that you can use to populate this. And then we've also added in 6.0 DL breach, which is a quasi-physical kind of mechanistic approach where you actually put in the soils data, and the model will actually try to develop the breach on its own, which is really, really cool. But you should do it as just one of your portfolio of ways to come up with your breach. Okay, so then you define your computations and you run it. What's the number one? Okay, let's go back to the chat. What do you think the number one HEC response is when people send us their model, their unsteady flow model that isn't working? Good luck. I like that. That's amazing. Good luck. Time step. And if we're feeling generous, it's like, hey, you might want to use a smaller time step. If we're feeling ungenerous, it might be like, your time step is like 3 orders of magnitude too large. Start at 1 second and go down, right? Or compute a chronic condition. But in general, with dam breach, 30 seconds is almost unheard of high. Generally you're going to be in the single digit second or sub single digit second time frame. And of course, in 6.0, you can go down to 0.1 seconds, but you can actually go a lot finer than that, because you can turn, if you turn on current control, it'll compute sub 0.1 second time steps. Of course, if you're sub 0.1 seconds, you might want to think about your mesh. But I do a lot of flume, a lot of sediment flume work, and sometimes we just need to be down there. Okay, and then finally, how do you look at results? So I don't love doing this in PowerPoint, so let's just do this in RAS. And so here we've got our model, and kind of the first thing, the thing that is breach specific, you've been seeing, so the mapper tools are amazing, and you've been playing around with them, and we've been demonstrating them. But there's a couple things we have to talk about before we get to mapper, is that if your model has a 2D connection or an inline structure, which all of the different approaches that we've described do, then you actually have 1D features in your model. And so before we even go to mapper, you can either go to view, and I never use these menus, so I have trouble finding them, but you can go to stage and flow hydrographs, or you can just push the hydrograph button. And this is all in .NET in 6.0, so it's all new. If you're used to these, they're different now. And we can just, if we go to type, you can actually look at, hey, what's going on in the storage area? Or you can say, hey, what's going on with my storage area 2D connection? And this is a really helpful tool to say, hey, your flow is increasing with spillway flow, and then boom, you get your breach. But Anton has actually added a breach specific visualization tool, which I understand you've already had your hands on, but let's just open it again. It's this button that shows a breach mid formation, which just adds a little bit of general anxiety to our main page interface. And this gives you the kind of the main things that you would be interested in: the breach width formation, the velocity through the breach, which is particularly important if you're using the simplified physical, and these kind of standard flow stage hydrographs that we're interested in. And so these these sorts of things can help you kind of dial in, particularly if you're using DL breach or the simplified physical, to look at, hey, how is my breach progressing? Does that make sense? And there's a couple of gotchas that you can, a couple of like classic modeling failure modes. I talk about 4 of them in the video tonight. It does seem like I covered a lot of material in a 28-minute video. I challenge you to listen to me at 1.75. Okay, and then if you go to Mapper, you can do all the cool Mapper stuff, right? The Mapper stuff is not breach specific, but the kinds of things that you'd want to do, obviously, you want to animate. And so here I've got a velocity. Here I've got a velocity map, and we're gonna watch the velocity map of the breach. And you can press the turtle. This is classic RAS team humor. You can press the turtle to get a slower breach, but the time step is such that you don't really need to do that here. Then if you right click on any node, you can get a time series of whatever it is that you're displaying. And so here we're looking at a time series of spillway velocity, which gets up to 13 feet per second, which that's pretty interesting for spillway design. You know, Orville's really made us all very sensitive to our spillway velocities. But you know, we had some anxiety about some of the Missouri structures during 2019, and so that's a pretty helpful output. And then you can go to the profile lines, and I've created a kind of small center line here that I've just digitized it along the line here. And you can come in and say, hey, I want to plot my velocity, or I want to plot my velocity against terrain. And you can see this is, it gives you the standard 1D profile that you'd be interested in, but also gives you these like velocity zones that I think is, you know, for these kind of analyses, this is a really interesting and helpful result. And of course, it does also animate with your model, which can I know we probably have some managers on the call, so don't take this the wrong way, but some eye candy for managers.